So we'll do problems from chapter 11. Okay. What is the direction of the velocity if a negative charge that experiences the magnetic force shown in each of these cases, assuming it moves perpendicular to B? Okay. So the force on a charged particle is Q V cross B. Yeah. So what we can do is we can use the right-hand rule, figure out what direction a positive charge needs to move to get that force. Okay, so the magnetic field is coming out of the sheet, and you see if it's coming out of the sheet. Okay, a positive charge moving in this direction, V positive charge moving in that direction will give you a force in that direction. V cross B will give you a force in that direction. So a negative charge needs to be moving in this direction to give you that same force. Okay? All right, so that's the idea. You have to figure these out. Okay, I'll do one more, and then I'll let you guys figure out the other one. So the magnetic field is into the sheet, and the force needs to be in this direction. So the velocity needs to be, for a positive charge, the velocity needs to be in that direction. Okay, so a negative charge will have to move in the opposite direction to have the same force. Okay. The best thing to do is turn a screw from V to B. And that's the best way to figure it out. Okay. A cosmic ray proton moves towards Earth at 5 times 10 to the 7 meters per second. A cosmic ray proton is a proton from a far, far away source. Okay. Experiences a magnetic force of magnitude 1.7 times 10 to the minus 16 newtons. What is the strength of the magnetic field if there's a 45-degree angle between it and the proton's velocity? Okay. So again, the magnetic force is Q V cross B, and the magnitude of the force is Q V B sine theta, where theta is the angle between the velocity vector and the magnetic field vector. Okay, so they give you the angle to be 45 degrees, and they give you the magnitude of the force. So B is F Q V sine theta. Okay. And the force is 1.7 times 10 to the minus 16 newtons. The charge of the proton is 1.6 times 10 to the minus 19 coulombs. The velocity is 5 times 10 to the 7 meters per second, and sine 45. So let's take care of powers of 10. That's 10 minus 3. That leaves 10 minus 10 to the 4. And then when that comes, that becomes 10 minus 4. Okay. And this will work out in Tesla. And that's a good thing. See, this is the order of the Earth's magnetic field. Okay, and this is happening on Earth. So we have the right magnitude. So this is 1.7 divided by 1.6 times 5 times sine 45. 0.3 into 10 to the minus 4 Tesla. And 10 to the minus 4 Tesla is a Gauss, so 0.3 Gauss. Okay. So that's the magnetic field. Okay, a cosmic ray electron moves at 7.5 times 10 to the 6 meters per second, perpendicular to the Earth's magnetic field at an altitude where the field strength is a tenth of a Gauss. What is the radius of the circular path the electron follows? Okay, so let's say the Earth's magnetic field is like that. Let's figure out the path of the electron. So let's say here's the electron. If it moves in this direction, V cross B would be if this was a positive charge, the force would be in that direction. This is a negative charge, the force will be in this direction. And so this electron would make a circle like that. Okay, so it would go in a circular orbit like that. So if the magnetic field is into the sheet and you throw an electron upwards, it will make a clockwise circle. And you saw that QVB will equal mv squared by r. Yeah. So r is mv or qb. So that's the radius of the circle, and it's an electron. The mass of the electron is 9.11 times 10 to the minus 31 kgs. Velocity is 7.5 into 10 to the power 6 meters per second. The charge of the electron is 1.6 times 10 to the minus 19 coulomb, and the field is 10 to the minus 5 Tesla. Okay, let's take care of powers of 10. That's 10 to the minus 25. This is 10 minus 24, so you get 10 minus 1. So this is 9.11 into 10 minus 1 into 7.5 divided by 1.6. And this will come out in meters. So roughly the radius is the size of this room, again, or to the roof. Okay, so horizontally it's making a circle half as big as this room. Okay. So, well, it's going like this. The magnetic field in this room is in that direction. Okay, and the speed is about the speed of light is 3 times 10 to the 8 meters per second, so roughly 2% the speed of light. Okay, so this was in the old days when they had CRT cathode ray tubes for TVs. An electron in a TV CRT moves with a speed of 6 times 10 to the 7 meters per second in a direction perpendicular to the Earth's field, which has a strength of 5 times 10 to the minus 5 Tesla. What strength electric field must be applied perpendicular to the Earth's field to make the electron move in a straight line? Okay, so here's the velocity selector. Well, here's the electric field, and let's say you have the magnetic field there's the magnetic field. and you want the electron to move in a straight line, okay? So the velocity selector is E over B, okay? And so what are you given? So the electric field that you need is V times B. So part A, V, the velocity of the electron is 6 times 10 to the 7 meters per second. And B is 5 times 10 to the minus 5 Tesla. Okay, 30 into 10 to the power 2, and this will be volts per meter. So the electric field needs to be that strong. So what we have to do is, if this were 1 meter apart, you need 3,000 volts applied. And if it's 1 centimeter apart, you need 30 volts applied between the plates. Okay. If this is done between plates separated by 1 centimeter, there you go. What is the applied voltage? Okay, so part B, voltage equal to E times D, so voltage is 3,000 volts per meter times D is 0.01 meter, 30 volts. Okay. By the way, this is voltage, and that's the units. Okay. Okay, this problem says a wire carrying a 30 amp current passes between the poles of a strong magnet that is perpendicular to its field. So let's say here's the field, and you have a wire carrying a current. So what is the direction of the force on this guy? The force on the wire is given by I L cross B. L is the length of the wire, so L cross B, the force will be in this direction. Okay. Okay. Wire carrying a 30 amp current passes between the poles of a strong magnet that is perpendicular to its field and experiences a 2.16 Newton force on the 4 centimeter length wire in the field. What is the average field strength? So the magnitude of this force is ILB, since the L and B are perpendicular to each other, and B is F over IL. 2.16 newtons divided by 30 amp, and the length that is relevant is the portion just in the magnetic field. Is there a force on the wire that is not in the magnetic field? See, if you're not in the magnetic field, there's no force. Okay, so only the charges that are in the presence of a magnetic field, they feel a force. Okay. All right, L is 4 centimeters, 4 into 10 to the minus 2 meters. Okay, so this is 216 divided by 120. So the magnetic field is B is 1.8 Tesla. That's a very strong field. Okay. What is the maximum torque on a 150 turn square loop of wire 18 centimeters on the side that carries a 50 amp current. Okay. So here's a square loop of wire. It has 150 turns. What is the maximum torque? So there is the I, and let's say it's in the presence of a magnetic field like that. Okay, what is going to happen? So here's the torque, here's the loop, and there's the magnetic field. That's when the torque is maximum. So this is an electromagnet, there's the magnet, and it is going to turn toward the magnetic field. Okay. The torque is given by mu cross B. What is mu? That's the magnetic moment, how strong of a magnet this is. Okay. And mu is n, the number of turns, times I times the area vector. So in our case, the area vector is in this direction. Okay. It is just the area of the loop. Okay. And how did they figure out the direction of the area vector? You point your fingers in the direction of the current, and your thumb is pointing in the direction of the vector. All right. So anyway, so when these two guys are perpendicular to each other, that's when the torque is max, and the max torque is NIA times B. Okay. So theta is 90 degrees between them. Okay, so we have 150 turns. Current is 50 amp current, that's a large current. Area is 0.18 meters square, and the field is 1.6 Tesla, and that's a strong field. So the maximum torque is okay. So this is how electric vehicles get torque. Okay? Except that in an electric vehicle, in an electric motor, you can't have a field that strong. You probably have a field, I'm not sure, maybe 1/100th of that. So the number of loops has to be greater. Okay. Number of loops is much greater. Okay. In this problem, a proton has a magnetic field due to its spin. Okay. So what was this guy? This was an electromagnet. Anytime you have a moving charge, you produce a magnetic field. Okay. So a spinning proton is also a moving charge. So let's say a proton is spinning like that, and a proton is positively charged. So a proton has a magnetic field due to its spin. The field is similar to that created by a circular current loop of 0.65 times 10 to the minus 15 meters. See, that's a femtometer. And so this is roughly the size of a proton is what they're saying, is the radius, with a current of 1.05 times 10 to the 4 amps. Okay. So they're modeling the spinning proton by a loop of current, and the current is 10,000 amps. Okay. Find the maximum torque on a proton in a 2.5 Tesla field. So let's say if the field is 2.5 Tesla, okay, that's the magnetic field in an MRI machine. So that was the MRI machine we didn't talk about. Okay, so they're using protons. Where do they have protons? Where do you have protons in your body? Every nuclei has plenty of protons, but they are using the protons of the hydrogen atom. Your body is full of water. Okay, so those are the protons that they're using. Okay, so what they do in an MRI machine is, okay, so what they're doing in a machine is, so here's a proton. Now I'm going to just give you a simplistic view. So when the magnetic moment is pointing in the direction of the magnetic field, the potential energy is the lowest. When it's pointing in the opposite direction, then the energy is highest. Okay, so there's mu and there's the magnetic field. This is a low energy state, and there's the magnetic field, and when the proton is pointing away, that's a high energy state. Okay. So what you do is, this energy difference. Okay, so I'm going to quickly go over this. The energy difference is proportional, is related to the magnetic field strength. Okay. So, slow me down if you're not understanding this. Okay. So, you can excite a proton from a low energy state to a high energy state by sending a photon of the right energy. Okay, so you excite a proton from a low energy state to a high energy state by sending a photon of the right energy. Okay, so you shine light of the right energy, and that photon gets excited. And that proton gets excited, meaning it spin flips. And then eventually it'll come back and emit that photon. And this is the photon with which you're going to take a picture. Okay? Did you guys understand that portion? All right. This energy level, remember, depends on the strength of the magnetic field. All right, now here's the mystery. So here's your brain. You want to take a picture of this spot in the brain, not any other spot. You want to take a picture of that spot. And the MRI machines can take a picture of spots about 0.5 millimeter size. And that'll depend. So how do you take a picture of that spot and not this spot? So I'm posing a question to you, since you guys are smart engineers and scientists. All right, so the energy level depends on the magnetic field. So what you have to do is make the magnetic field different at every location. And so at the spot where the magnetic field has the right value, only those spots will absorb these photons. Those photons are absorbed by only where the energy difference is right. So that spot absorbs photons, and then you take a picture of that. And then you want to take the picture of the next spot, so you change the magnetic field accordingly. So what do? You take a picture of 1,000,000 spots, and then you have a computer, and have the computer put together all the. That's your MRI machine. All right, so let's go back to that. So there's the MRI machine. So, by the way, so the field is pretty strong. See, this is a gurney that came flying across the room. I guess some person flipped the switch on the machine, turned the machine on without making sure that no metal was inside the room. Okay. So here's the proton, there's the magnetic field. This is the low energy state, there's the high energy state. Yeah. Magnetic use moments of protons, hydrogen nuclei for imaging. Yeah. Here's how so gradient magnets are turned on and off very rapidly in a specific manner, altering the magnetic field at a very local level. So right now you're taking a picture on the intersection of those three planes at that spot. That spot has the right magnetic field. Okay? And then once you take a picture of that spot, then you move to the next spot and so on. This allows one to pick exactly what point to take a picture of. Okay. Machines apply a specific energy RF pulse. So what that means is it's sending out a radio frequency pulse, which is consisting of photon, which only the right energy difference can absorb. And then when it de-excites, it'll emit that photon. And you're using that. Pulses cause proton in that area to absorb energy and jump to the higher level. This is the resonance part of the MRI, magnetic resonance imaging. And when this photon is emitted, that's the imaging part. Okay. When the RF pulse is turned off, protons begin to return to their natural alignment. They go from the excited state back to the ground state. Okay. By emitting the RF photons, by emitting that photon. The coil now picks up these photons and the information is transferred into an image. Yeah. Most imaging modalities use injectable contrasts or dyes for various procedures. MRI contrasts work by altering the local magnetic field in the tissue being examined. Okay, so remember, if normal and abnormal tissue respond differently to contrasts, allowing the visualization of tissue abnormalities and diseases. So diseased tissues react differently than normal tissues.
MRIs are very loud and make certain noises.
Mm-hmm.
Does that have anything to do with?
That's the current passing through to produce this magnetic field, strong magnetic field. Okay, that's what the noise is going to do. Nowadays, these are superconducting. So you've had an MRI?
Yes.
Yeah. Are you claustrophobic?
Not really.
Mm-hmm. You are claustrophobic?
A little bit, yeah.
All right, let's do this problem. I'm getting tired. We'll end at this problem. Okay. We got sidetracked because of Courtney, so you can blame Courtney for this one. See, I didn't blame you today. It's a good day for you.
Thanks, Courtney.
Next time we'll blame somebody else. Okay. So a proton has a magnetic field due to its spin. The field is similar to that created by a circular current loop. Okay. And the current is that. Find the maximum torque in a 2.5 Tesla magnetic field. So the torque is given by mu cross B and max torque is mu times B. Okay. So the magnitude of the torque would be, okay, let's write magnitude of the torque would be B, mu B sine theta, where theta is the angle between mu and B, and so the max torque will be mu times B, and mu is I times area. Yeah. And this is a circular loop, so that. So now we can put in all these values, 1.4 times 10 to the 4 amps, pi r is 0.65 times 10 to the minus 15 meters square, and the field is 2.5 Tesla. All right, so that's 10 to the minus 30 plus 4, 10 to the minus 26. This is a torque, so it'll work out to Newton meters. And the rest is 1.05 times 0.65 square times 2.5. Okay. Okay, so that's the torque. That's a very small torque, but you're turning in a proton. That's very light, so that's plenty. Okay? All right, guys.